Okay, our last speaker today is Javora, who's going to talk to us about search. Thank you. Go ahead.
All right, can you hear me? Yeah, probably. All right, hello everybody. The title of this presentation is Voice Search Using NLP and CoreML. Originally, when I put this together, I thought I would be like edgy by using CoreML, but seeing everything that's happened since yesterday and dub, it seems like everybody and their dog is doing CoreML, so that's out the window. I work for a company called Kiwi.com, which is like an online travel agent and a search engine. Think Google, but for long-term, long distance travel. And once upon a hackathon, I decided that it would be cool to to be able to use voice search. So, what? We have like Kiwi.com started as a website, but over time we added mobile apps as well, and the mobile app looks sort of like this. It has all the regular things that you would expect. You pick where you want to go, when you want to go there, whether you want to return from that place or not, and you said how many people want to go, and you get some results. So you might ask yourself, like, why? Why would you want to search something like that using your voice? Well, the thing is that besides all these normal things that that you have in your search, there's also a whole bunch more. You get to pick how many bags you want to take with you. You can pick several destinations or several starting points even, and you can do like multiple ranges in the calendar over there. Once you get your results, you might want to filter them somewhat. Pick if you want to have a direct flight, or the maximum duration for your journey, or if you want to sort with something. And also, you can have more filters. You can pick departure times. You can pick which mode of transportation you want. You can pick your carriers that you want or do not want. I don't know about you, but that seems like a lot of options. And it might be that it takes time, to click all those, to pick exactly what you want. The interface is very simple, and you can certainly do it, but it might get too long. So that was one of the motivations. Another was that we realized that the controls you can see here are all over the screen, and you might, for example, have like smaller hands and a giant phone. For some reason, everybody wants giant phones these days. And besides that, while there are a lot of people in the world who see the slides exactly as you do now, there are some people who, might not have the perfect vision. So you might instead see something like this. And what drove this home for me was yesterday's excellent demo of voice control in iOS 13. If the OS lets you do everything just with your voice, we can at least optimize this one part. So what I tried to do was make all these selections, use all these filters just by speaking one sentence to the app. And so how would you do that? I have to confess that I'm not an expert in this stuff. I'm a normal iOS developer. I do I do layouts, I do logic, sure, but I've never worked with voice or speech recognition or any of that stuff. But I think I have enough like skill to divide problems into smaller chunks. So in this particular case, you have you need to get the input from the user in by way of their voice. You need to transcribe that voice into text, and then you need to pick out the interesting information from that text. So the first part, of course, is recording the speech. And fortunately, it turns out Apple has sample code for exactly that. Not just for recording, but also for transcribing it in live speech. So I didn't have much to do there. The frameworks that are used are AV Foundation for the recording, and the speech framework, which is iOS only, unlike AV Foundation. And you know, just tweaking that sample code for like an hour, I got something that worked pretty much the way I wanted it to. The one thing that's a bit unfortunate is that if we want to do this, iOS requires several privacy descriptions that you have to add to your play-list. First is the reason why you're using the microphone, and the second is why you are using speech recognition, which unfortunately results in the user having to click both of those dialogues basically right after each other. So that's not ideal user experience, but there's probably nothing we can do about that until Apple, or unless Apple changes their approach to showing these dialogues. It is also interesting to note that it seems, at least in all of my experiments, that the transcription works on device in English, and I believe Apple said yesterday that starting in iOS 13 that will always be the case. Prior to that, they always advised developers to assume that an internet connection is required, but it's apparently not for this part, at least in English. And so there are just like a few interesting things here regarding speech recognition. You have to pick the language up front. You cannot, at least I believe it is not possible for iOS to recognize the language that the user is speaking just from the sentence. And also, once you do the recognition request, you can specify whether or not you are interested in partial results, which that's the thing where in Siri you start speaking something and the words appear one at a time. So that's partial results, which here is kind of useful for determining when the user is done speaking, actually. So that was quite easy, this part, but I soon learned that you know, even though it looked like a 3-step process, that's by no means even. Like it's not 66% done at this point, and the main problem, of course, is the parsing of the text. So I set myself like this goal of having this sentence be recognized by the app and do all the right things. And that's split into those 5 segments there. So what I decided to do was start with one and have it work, then move on to the next one. And so let's start with the first one. The simplest form of the sentence, at least something that's useful, would be to identify the destination, where the user wants to go. And for that, I've reduced this sentence to just find flights to Chicago, where the Chicago part is the important one. But again, like I have no idea how to do this. Like I had no idea at the time, at least. So you know, I just looked at the sentence and did the simplest thing possible. and that would be just to find 2 and assume that everything that went after it was actual destination, which it works for that one sentence, but that's about it. Like if you, for example, move on to the next segment there, and you try that approach with this sentence, where you also specify the departure date, you suddenly get Chicago next Monday for the destination, and that's not very useful. We could also do it like just have the next word after the 2 be the destination, but that would of course not work for places like New York City or even San Jose. So that wasn't the way. And but I thought, this is natural language analysis, and thinking back to previous DubDub, Apple introduced something that could help us out here, and that was called the Natural Language Framework, which can be used to do analysis of natural language, obviously. So I looked at it, and the NL tagger class is exactly what we want, because it can it takes a string as an input, and it assigns tags to individual words, or maybe even some other bits, but words are important for this case. And there are multiple schemes that it can be configured with. Once I saw this list, I of course knew that the name type will be the interesting one there, because that, according to the documentation, NL tagger can then identify personal names, place names, and organization names. So the code for setting that up looks something like this. We initialize the tagger. We give it some schemes that we want it to recognize. And then we enumerate the tags in the sentence. And if the tag matches our place name, then we just add it to the array. And finally, we just join everything together. And this works because the tagger correctly recognizes Chicago as a place name. It recognizes New York as a place name. And so, yay, finally, something that works. Mission accomplished, at least 1 out of 5 anyway. So the next challenge was to somehow have it parse dates. And if you look back at the schemes here, there's nothing like that, unfortunately. So I briefly thought about using date formatter for this, because there's a property on date formatter called, I believe, does relative time formatting or something like that, or date formatting. But unfortunately, that only works in the opposite direction, where given a date, it will produce naturally sounding things like next Monday, but or tomorrow, or stuff like that. But it cannot work in the direction that we want. But if you've been using Apple devices or Apple messaging apps or that sort of thing in the past few years, you will know that when you write stuff like that, for example, here in Notes, the dates highlight or underline anyway. And if you search the web, you can find out why this is, or rather how it is implemented. It is done using a type called NSData detector, which besides dates can also identify websites, phone numbers, addresses, all sorts of other things. But the only thing that we need from it are dates. And so this is how you might use an NSData detector for this. The initializer suffers from some Objective-C not very nice Swift type. But once it is initialized with the date, you can see the chicken date in the second line there, we can just find matches in the string and take the first date, which in our case is next Monday, and it works. It even works on the entire sentence. It doesn't work on just a substring from that, which is great. And the other great thing is that it works on these relative dates as well. It works on precise dates, like if you say the 24th of June, it will also work in any format, but it also works for these relative dates. So yes, good. We now have 2 out of 5, so let's go on to origin, because some people care where they're coming from. And unfortunately, this is where my very, very simplistic attempts hit a wall, because I've so far assumed that there was only one of each of the things that we need to parse in the sentence. Suddenly, here we have 2 places. We have London and Chicago. And we have no reliable way of telling which is which, which one is the origin, which one is the destination. The NL tagger will tell us that there are 2 places, but that's all it can do at this point. We could use the words from and to indicate which is which, but that doesn't always work, because one could ask for tickets between London and Chicago, and suddenly we have no markers. We could also use the order and assume that the origin is always the first, but that might not always work. And one of the goals that I set for myself here was that I want I want the user to have the most freedom to not have to learn the syntax, but to say whatever they want. So I thought about this for a while, and I got nothing. And I told a colleague who looked like he was thinking for like 5 seconds, and then he came up with the answer. And what he said was, "Why don't you try machine learning?" Well, I had heard of machine learning before that point. I knew that Apple was using it for a lot of stuff in iOS, and I knew that it could identify things in pictures, but that was about it. But as I started learning more and more about it, I realized that it is that it does exactly what I needed to do for this problem. Because what machine learning does, at least in my limited understanding, is that it makes predictions from data. So if you somehow don't know how Apple's machine learning works, because there seem to be tutorials everywhere now, there are 2 parts. There is the Create ML framework, which creates the models. And then there is CoreML, which actually uses those models to predict stuff. Apple has sample code for this as well, but they're using their very pretty UI in Playgrounds. And that, as far as I know, only works for images and not text. So what we want from our model is to be able to, given some sentences that the user might say, we want to it to predict what the user might have meant. Specifically, which words mean what, like what categories they are, like if they're places, if they're dates, and maybe some other stuff later. So to try to start making a model, we need some inputs, some samples, and in this case there will be sentences that the user might say. I've chosen these 6 for, well, because they're, at least to me, quite representative. And what we need to do once we have these sentences is to tell the model what each part of them means. And so taking the first sentence here, we will split it into words. And for each word, we will give it a tag, which might look something like this. Most importantly, here is the highlighted part of what's actually of the interesting ones right now. And it doesn't matter if that they're split into words. What matters are the patterns. So if we have like multi-word declaration of the date here, like the 11th of February, we will simply tag each word with date, which is like the tag could be anything. We just need something to say that it's a date, and why not just use the word itself? And we use Prague and Spain as places. We need to somehow get this into code. So the way we do that, at least in this instance, is using JSON. And so we create an array with objects. Each of the objects has tokens and labels as arrays, and they are exactly what you saw on the previous slide. Tokens represent the actual words, and labels are the tags. Once we have that for all of the sentences, we can actually create a model. We load that JSON from the previous slide. We attempt to create a word tagger with the data. We tell CoreML, or CreateML actually, which column is which. We assign some metadata because, I don't know, Apple thought it was important. And we finally write the model to a file on disk. Once we have that, we can actually plug it back into our NL tagger that we used earlier. We create a custom scheme. We assign that scheme to a tagger. And we create the model, which once you add to an Xcode project will auto-generate like 200 lines of code for our code to interface with. And we set the models for the scheme. And finally, we create instances of NL tag that we can then compare to the previous, that we can compare to the tokens that we have in the model. So here it's place and date. And once we have that, our model will be able to recognize both dates and places from those 6 sentences that we had before. But that didn't actually solve anything because we still don't know which direction is which. So, but that doesn't matter very much because this was the hard part. From now on, every time we want to actually add more data or improve the model, we can just assign more tags to our sentences. So if we want to know which direction the user meant, we will just go back to our sentences and pick the from and to and give it new tags. And of course, if we had sentences with, like I said, between X and Y, we could also apply these tags to them. And what we do then is we scan the sentence from back to front. We look for the first of these direction tags, either from or to, and we then go further back and look for the other one. And whichever one is more to, whichever one is first, we assign that, well, whichever one is closest to the back of the sentence, we take everything after it and we say that that's the value of the tag, and the one between the two tags is the value of the other one. And with that, our sentence will now work because the model recognizes both from and to as specifying the direction. And our place tag recognizes these places for what they are. And finally, we can just as easily have it recognize return flights by just adding yet another tag. Here, we've just added the one word, return. And we'll just go back to our sentences and use return to mark it as a tag in all sentences. And if the way that we determine whether the user wants a return flight or not is just by looking for that tag, and if it's present, we say that it is. And if it's not, then we'll just make a one-way flight. So this is just a few of the many things that we can add. And I haven't gotten here yet, but it seems very interesting to me that we can achieve all of this with just this tiny model. I mean, I don't know if you've seen the Apple Design Awards this year, but one of the apps used a model with, I think, 90,000 sentences. But we can quite reliably make these search queries with just 6. So I think that's pretty impressive. The actual model that we're using now in the app has about 30 sentences, and it supports date ranges as well. And also, I think, sorting, but I'm not really sure about that. Another thing that I find very interesting about this is that if it so happens that the model doesn't do exactly what you want, the only thing that you need is to just add more sentences that are representative of what you would like it to do. For example, we had a problem with when adding the date ranges, then that a user might say to look for flights from June the 10th to August the 2nd, and then the model would get confused because we're using from and to for both date and time. But the solution, as I said, was simple. I just added more sentences that basically convinced it that this is the right, what is the right solution. So I think I'm done here. Do you have any questions?
We have, let me give you the mic.
Hi. So how much of the NLP did you actually end up using at the end of it, or was it all machine learning?
I'm sorry, I didn't catch that.
Sorry. I'll say that again. So how much NLP did you have in the final product, or was it all machine learning?
Well, the NLP part, at least to me, is using the natural language framework for identifying this stuff. If you consider that only machine learning, then I guess the answer is not a lot.
Hi, I was just sort of curious to see how happy you were with the results of the speech recognition library provided, specifically just for your domain, if it had, a hard time understanding some of the places in your test or whatnot, or just how well it worked out for you.
Right. I believe that there is actually some machine learning going on even in recognizing the speech. This is all done using Apple's frameworks in iOS, because I mean, I had the same concerns because I suspected that this would work well for American names, perhaps British names, and like the major languages like German and French. But it just worked. We're from a city called Brno, which you probably never heard of, and it just recognized it. Possibly, I mean, when you look at the transcribed speech, it normally capitalized the name of the town. So I guess it is that smart. There was no problem with this.
Well, great.
Actually, what I found more interesting was that when not using a custom-made model, the Apple scheme, the name scheme, picked up San Francisco not as a place, but as a person, like as a personal name, which I wouldn't expect, from Apple being from around here, but.
Any other questions? Yep.
This might be a little bit outside your domain, and if it is, that's okay. Just let me know. The user experience around the confidence of the returned results, like let's say you're in a noisy environment and the confidence level you got back from speech framework was lower. Did you, how did you solve that, or is that something you just say download the app and find out?
Right. Actually, I didn't have to solve that problem yet because this is not yet in the shipping product. So I will leave that to our designers, I think. Currently, my toy implementation just does nothing when it's not confident enough.
I was just wanting to know, I saw how you had everything hard-coded in there in terms of building out your tags. What other method would you have besides hard-coding in your tags?
Other methods for what?
You had your tags, you said equal, whatever,
Yes.
destination. But I'm asking, I'm sure the possibility that, as you mentioned, someone had like 1,000, whatever, associations there. So you're telling me that you just put it in there hard-coded as you illustrated?
Well, the tags in the model, they have to be hard-coded. There's no other way to do that. I mean, the only part that we operate on is basically this, the collection of the tags themselves. This method runs through the entire sentence and tries to match a tag to every word. And all the algorithm basically is here, or would be here. The closest thing to that I described was how we pick out which place is the origin and which is the destination. But besides that, I'm not sure.
Because when you were showing that model description, you had things hard-coded in. And what I was asking, is everything hard-coded?
Yes.
Any other questions? Anybody? All right, thank you.